let we continue this lecture. Before this, we discussed on the seismic refraction. So the use of seismic refraction is can able to determine the depth of boundary between soil and rocks, or soil profile of each geophone, and then you can check the any anomalous condition on the area along this survey line. So, for example, you have 115 meter geophone you lay between geophone 1 and 24. So then along this line, you can see this soil profile, boundaries between rock and soil, able to see any fraction orientation. If you can see the velocity changing, so sometimes because of the fraction. In the rock fracture, the velocity is the rock. If you have solid rock, so the velocity is increased. And then advantage, we able to measure up to 35 meters. Sometimes if you want to have a greater depth, you can use explosive. This one is based on the using sledgehammer, and then you can get 4 to 4 layers of soil, and then they can provide depth for each geophone. And then this example that I show is using the P wave, compressive wave, but also can use the S wave. Okay, S is shear wave. After this, we will discuss what is the differences between P wave, S wave, and type of wave later. So, and then we discuss the advantage is using the simple source hammer, seismic hammer, seismic source, which is using slash hammer. Yeah. So disadvantage, sometimes the survey length, we have 115 meters length survey. We just get up to 30, sometimes 35, based on depend on the site conditions. Require intrusive contact means we need to we have to install our geophone or to the ground, and then it's sensitive to the noise or vibration. So mean that if you do this testing near to this highway or roads, so we have problem, you have to stop the traffics, and then seismic layer must be okay. This is the principle of the seismic refraction. The seismic velocity must be increased with them. So mean with that must be increased. So if we have layer like this, this is our ground. This is our ground. We have our ground here. So let's see, we have a soft layer here. This hard. Let's see, this velocity is 1000. Then we have 500, and then we get another 1000. Let's say 1500. So this layer will be as good because this is, we call them soft layer, thin soft layer. We cannot able to detect this layer because this decrease in velocity. And then deeper measurement, you require explosive, and very deep information. That's why in oil exploration they use explosive and longer line of survey line, very long, up to 1 kilometer sometimes. Then we move to seismic refraction. It's another technique using seismic wave. They're using the measure time travel seismic wave, and that reflected because of different density. Try to remember the video that I'm showing you, and then they're reflected because of different density or hardness of stiffness, and then the wave continue, the rest of wave to continue to propagate to deeper layer. Then the time travel of seismic wave is function of soil density, hardness, and the stiffness. So for example, like this, you have this is normally we use on the oil exploration. Normally they use seismic reflection. So they have hydrophone, mean that geophone type of geophone that they can use apply in water, put in water, and then they tie on the vessel and then they pull it. So they have air gun or they use explosive, so they can get the pattern of the wave that captured by this hydrophone. Based on that pattern of this wave, this is how they reflected, the strength of reflected. The strength means the how this the the amplitude of this wave. And this talking about amplitude. If you have big difference, so we have very big high reflections, amplitude. So the contrast, so the better the amplitude. So mean here, based on this amplitude across the survey line, we can check the profile, this soil layer. Yeah, this is how they interpret this ground based on the reflection. Okay, and to confirm that, they have to do this deep borehole, and you can confirm these informations. So meaning that this seismic reflection able to determine very deep, because then they're not then able to determine the thickness and structural geology. And then the advantage, because they can provide high resolution cross section, high resolution along the cross section, and then measurement up to 350 meter depth using 10 pound. If you use explosive, they can go up to maybe 1 kilometer depth. Okay, survey. So the survey line length source is okay. The survey line source to the farthest geophone is usually 1 or 2 times of desired depth size. Okay. Disadvantage require intrusive contact on the ground, sensitive acoustic, similar, and then require extensive seismic processing. So for this seismic reflection is involve a lot of seismic processing, wave processing. So before we end of this technique, so better you understand technique and the seismic type. In the seismic type, we have a few types. We call that P wave, compression wave. Call that, sometimes we call it primary wave. We got S wave, call it secondary wave or shear wave, and another we call it surface wave or R wave, Rayleigh wave. Yeah, the speed between these material, if we have similar materials, for example, we have rocks, granite. Let's see granite here. So when we measure the velocity, the speed of the granite is 3000 for P wave. So for secondary wave, normally half of that, 1500. So for surface wave, is reduced to 1000 based on this proportion. You can calculate. Maybe is up to 1300 meter per second for the surface wave. So meaning that the speed of velocity decrease based on the type of wave. Why is decrease? Because of the way they propagate. Okay, this is the example of wave, type of seismic wave. In the seismic wave can generate by our sledgehammer. The big one is come from the earthquake. Earthquake produce seismic wave. They're able to shake or damage our building because of that wave. Okay, see how the wave influence the factor of damage of the building. So it depends on type of ground and type of wave. You look on this video.
The motion of similar buildings on different bedrock will be exaggerated to show the arrival of compressive P, shearing S, and rolling surface waves from a regional earthquake. 3 consecutive seismograms will show the changing frequency and amplitude resulting from the change in rock type. The initial P wave arrives with a compressive bump and rarely causes much damage. The slower shearing S wave introduces a side-to-side motion that can throw loose objects to the floor and may crack walls. The rolling surface waves are the most damaging in unconsolidated sediment. As surface waves enter the sedimentary layer, they slow down and increase in size, causing buildings to roll. If not engineered for the motion, they can crack and tumble. But even a well-engineered building can sink during the shaking and liquefaction of underlying wet sediment. The first seismogram from the pink building on solid ground shows low amplitude, high frequency waves. When the waves hit softer ground, they slow down and increase in amplitude. It's this higher slowing roll that is so destructive during an earthquake.
So based on this video shows that if we have a low, this is show P wave, S wave, surface wave. So means this is more P waves come earlier than S wave and really surface wave. So the slowest is come later after event of earthquake. But they check on the amplitude here. See the amplitude. The amplitude here. See the amplitude. This P wave. The surface wave in the rock is the amplitude is lower than in the ground. But compared to this here, this is soft ground compared to the hard rocks. So the amplification of this amplitude will be occur similar, same source, but amplification happen because that material, the ground is soft. Make this the soil will be amplify the wave. Okay, that's why this is how the propagation of compression wave, like a spring. Okay, but if we have shear wave, this shear wave like this, and then if the rally wave is like this, rolling wave, call it, sometimes we call it rolling wave. This is a surface wave, shear wave. This is okay, shear wave, P wave, P wave. So if we have if you construct our material on the hard rock, let's say this hard, this hard, this soft, this soft. If you build our building in the hard ground, normally the amplification is not occur, but in the soft ground, see the amplification of this surface wave will be on the soft material. So if you have a earthquake somewhere, this is the epicenter here, so propagation of wave happen, and then what happen is to the ground is the amplification of this wave on the surface wave. Yeah. So to avoid this increase to reduce the amplification of wave, then you have to increase the strength or stiffness of material by doing this. This example here is dynamic compaction, or sometimes you can use column, stone column, or any technique of the ground improvement to improve, strengthen the soil.